Welcome back, ladies and gentlemen. It's been a bit. Hopefully you guys found some success with the one-dimensional dynamics. Right now we're going to be talking about two-dimensional dynamics, which means that we're going to talk about forces on an angle. So, the main thing we're going to see here is that forces on an angle are not actually that different from forces not on an angle. Just because I add both the vertical and the horizontal, the y vertical and horizontal x, doesn't really change anything. It's still the same basic plan. I'm still adding all the vectors together. The difference is just kind of what it looks like. Before, I'd have a situation that I'd have a box of some form. Maybe it was on a surface. And then I would apply some kind of force, like so. And I would have a force of gravity pulling down because I'm on Earth. And I would have some kind of force normal pointing up because the table wasn't collapsing. And I'd have some kind of force of friction going backwards. And when we had to work with these kind of problems, we would be doing very basic addition, right? We'd say, okay, the sum of all forces in the horizontal is going to be equal to, and then I just added the two numbers together, right? And I'd be adding numbers together, whatever they were. Maybe it'd be FA, which I see here is positive, and it would be F mu, which is negative in this particular case. And I could do exactly the same thing for the sum of forces in the y. I add them together, and I just simply have different colors. I'm talking about different forces. So it's Fn, which is up, and Fg, which is down. So this is everything that we were doing with 1D. All of this. So now we're going to change it. Now we're going to go with 2D. And what we're going to see is that it doesn't actually make that big of a change. Yeah, there is a change, but it's not that big of one. In a 2D system, we're going to have a box on top of a surface, and the force applied might be at an angle. And that's the only real difference. Think about the other three forces, right? Force of gravity, that one's easy. Force of gravity always points to the center of the Earth, so it's still going to be pointing straight down. The force normal is going to oppose the force of gravity, because otherwise the object's going to fall through the floor. And the force of friction is going to be working in some form parallel to the surface, right? So it's going to work going backwards, because the force of friction is between the two surfaces, right? Put another way, if I take this handy elastic band, and I make a real quick demonstration here. Here's my object. It is sitting here on the surface. Before, we were pulling it straight across, and the friction was going backwards that way. Well, we're not doing that anymore. Now, I am pulling it upward like this at an angle. It still goes this way, though, which means friction still points that way. But the fact that I'm pulling up at an angle is going to make a small change. But it's still adding. I'm not doing anything different. So, when I come over here and try to do the addition, how is it going to look? Well, the sum of forces in the x, I still have friction. Friction hasn't changed, so I can put that in. Negative force of friction. Okay. But now what do I do with force applied? Right? Force applied has got something else going on here. When have we seen this? Let's think this through. I have mentioned in class before, and unfortunately you guys haven't had the chance to hear it every single day, but when confronted with a new problem, turn it into an old problem you already know how to do. What do we do in 2 dimensions in kinematics? Pythagoras, trig. Everything's the same here. Just because it's dynamics doesn't mean that vectors have changed. And these are still vectors. So, FAX, FAY. And that's the big change. It's not much of a change, admittedly, right? It's just f(ax), f(ay), but it is enough of a change for what we're dealing with here. Of the vectors, the blue vectors, fa does not point in the horizontal direction. Fay does not point in the horizontal direction. Fax does. So whereas in 1D it was just fa, boom, done, now we have to say which vector points left or right. And that's all this is. Which vector points left or right. So fax. And it's going to be pointing right. And there we go. That's how we set that up. Now, what else do we have to look at? Well, we've also got fy. If we look at fy, the system hasn't really changed that much, right? There's still an fg pointing down, so I can still go minus fg. There's still an fn pointing up, so I can still go plus fn. But we're not fully done, because there's another vector pointing up, fay. Fay is part of this puzzle. And that's for the very simple reason that it points up. If it points up, I include it in the sum, because that's what a sum is. I'm telling you to add everything. I mentioned in the start of dynamics that this is the part that everyone struggles with. I have to add, but I don't know what to add. Yeah, you do. Everything that goes up or down is added in the sum of y, because y is up or down. Anything that goes left or right is added in the sum of x, because that's what it means. It means add everything in x. That's it. That's all you do. So this is 2D. And every particular question is going to have a slightly different way of using this. Every different question is going to have a slightly different setup, a different design, some kind of a difference in terms of how these things behave. And you are going to just have to learn to work with that. You're going to have to figure out how these things go, how they get put together, and what they mean. This particular question has a force applied, a force normal, a force of gravity, and a force of friction. Another question might not. Maybe it's a frictionless surface, in which case there's no friction. Or maybe it's not on a table, in which case there's no force normal. Whatever. Each question is unique, but all you have to do is add everything. There are a few little shortcut rules that we can remember. But realistically, we're just adding, nothing more and nothing less. But the shortcuts are going to be, they're shortcuts. They might be useful. The first shortcut is one that we've seen a lot, right? If acceleration equals 0, then what? What does that mean? In a one-dimensional problem, if acceleration equals 0, that means that the forces going left and right must be balanced, or 0, which is another form of balance. So that means that the sum of forces in the horizontal must be 0. That's still true. That's the same as 1D. Well, now look over there. What do we see? Well, if I make f of sum of x, right, sigma fx, if I make that 0, well then fax is equal to f mu. That's pretty much the same as before, right? Right? It's not that big of a difference if I write fa equals f mu. The only part that's new for 2D is I say fax. That's it. Now, the other place where things are going to be different is that, and this is key, this is going to be a key one, okay, is that we've already talked about if on a table Fn does not equal Fg. What? Why? It was like that for every single time in one-dimensional dynamics, but now that we're 2D, it's no longer true. Why? Well, if I'm on a table and I'm not going up or down, right, the table's supporting the weight of the object, that means that the sum of forces in the y equals 0. Well, look at our equation. The sum of forces in the y equals 0 is going to mean that Fn, Fay, and Fg are all involved. Now we should add one thing to this. If Fa points up, like our example does, then Fay will point up, which is what we see in our example. And if the question is exactly the same as our example, then we should get this relationship, because these two both point up and this one points down. That's the same thing that we got up here. So this is no longer true. This is true for one-dimensional, but this is 2D. So now it's a little more complicated because there are two things pointing up. The way you can sort of picture it is, if we again pull out our little example that I just quickly threw together, when I'm lifting up like this, I'm like partially lifting it off of the table here, right? Let's put it up a little higher, make it easier to see. I'm lifting it up. Like, this is an exaggeration, right? But here I'm lifting it as I move. Well, if I'm lifting it, it's got less contact with the surface. If there's less contact with the surface, that means that I'm going to have less friction. That also, put another way, it means that the table doesn't have to push as hard to hold it up because I'm doing some of the lifting. So what this means for you, when you've got to help your friend move, I told you this unit was going to help you with your friend moving, is that if you've got to, pull up, if you're lifting something up, right? If you're lifting it up, that means you're doing some of the work of carrying it. What happens if you push down, right? Our example here is with Fa going up and to the right? It's going upward at an angle. But what happens if I'm going down? What happens then? Let's see, right? The only real difference is I just changed the front. I'm going to have someone pulling down like this. Okay, what's that going to do? I still vector addition. Nothing has changed there. So it's going to be 1, 2, 3, 4, like so. F-A-X, F-A-Y. There's the change in the picture. Okay, does that change this at all? No, there's no difference, right? It's still this being positive and this being negative. So this part stays 100% the same. But what about this part? This is going to be different because now Fay is pointing down. It's negative. What does that mean, it's negative? Well, if Fay is negative, Fay is on the wrong side because this is no longer an up arrow. This is now a down arrow. So I'd have to move it to over here. And erase it from this side. So what does that mean? Why is it different now? Well, again, we're just adding, and we're adding all the arrows that point up and all the arrows that point down. Here's all the ups, here's all the downs. In this example, compared to the one I just erased, this is going down now. FAY is going down. I'm pushing this way. Well, it's down. It's different. It's going to behave differently. So what does this mean for my friend moving? Well, if you push down, you actually make it harder to move the object. Well, why? Why would I make it harder? Because you're putting more pressure, increasing the contact between the object and the surface. You're pressing it into the surface. More contact means more friction. More friction means you have to push harder in order to make it move. What this means for us is that when we're trying to help our friend move, if you are lifting up, if you're pulling it up, you will be able to carry it more easily because you're taking some of the weight, so you'll have less friction. If you are pushing down, you don't have to carry some of the weight, but you do have to push harder because you're increasing the friction. So you gotta choose what will work for you, and it doesn't make it any easier, unfortunately. One way or another, you're doing extra work. The question is, are you doing it with your legs or with your arms? Okay, this is all pretty abstract. So I'm going to pull up an example here from the notes. You guys have it already. You guys can give it a shot. So we got here this example. All right, so I'll just quickly sketch it out. We'll erase this and we'll work through the problem together. Then you guys, of course, are welcome to continue trying out these problems in the booklet. There is only one other part to the dynamics unit after this. After this is inclined planes, aka ramps. Once we get ramps out of the way, then, well, we're done dynamics. So you guys will have a test on two-dimensional dynamics, and we will move on to the next topic. But that's a little ways later. So right now, let's see what we can do. So our example that we're going to have from our notes, which means you guys do have it if you look at the notes in the drive. This is going to be a 16 kilogram object, and it's going to be located on a surface, and that surface is going to have a coefficient of friction of 0.44. Then we're going to have a force applied up at an angle, and it says this force applied is 150 newtons, and the angle here is 30 degrees. Now, that means it's going to be an FAX and an FAY. But that we'll get to later. We do know there's friction because it tells us there's a coefficient of friction. So that means this exists, but we don't know what the number is. What else does it tell us? Well, I'm on top of a table, which means that I'm going to have a force of gravity pointing down, and I'm going to have a force of normal pointing up. Is there anything else? Looks like no. So the question is, what will be the acceleration of this system? Okay, so that's what we're trying to find. So let's just make a quick note here that we're looking for the acceleration to make sure we don't lose track of what we're trying to solve. So to find the acceleration, I'm going to need to use sum of forces in the x is equal to mass times acceleration. Okay, I have the mass, so that checks out, but I don't have the force. Okay, so I can't solve this yet. So I'm going to solve for the force in the x, which in this case, I look at it and go, okay, the force in the x is going to be FAX minus force of friction, right? Because FAX points right, force of friction points left. Then I need to fill in some numbers. Okay, well, I don't really have FAX. I have FA, and I can get FAX, so why don't we do that, okay? FAX, well, this is just trig. So FAX is going to equal cos 30 times 150. Get out our trusty calculator. 30 cos times 150. We're going to get 130. Now, since we're already here, we may as well solve FAY because we're probably going to need it. And because we've already got the calculator out. So we're going to go 30 sine times 150. We're going to get 75 for that one. Okay? Hopefully you guys remember how to do this. You did a lot of it in kinematics. Okay, so that part, hopefully pretty clear. Then we look over here and we go, okay, I need this number. I have this number. I can put that in. That's 130. Minus, friction. I don't have friction. So now I got to get friction. Okay? So we know that the formula for friction is coefficient of friction is equal to, force of friction equal to coefficient times Fn. Okay, so the force of friction is what we want. The coefficient of friction, it tells us, is 0.44. And then Fn. Oh, okay, well, we know what to do there. We just simply have to do just like every other question, right? We just go that Fn equals Fg and call it a day. Except that won't work because it's 2D. If it's 2D, you cannot do that. That only works for 1D. Remember that point. That is the thing that's going to trip everyone up. I know it. It always does. Because you get so used to it. You're like, oh, every other time it's worked this way, but why isn't it working this way now? Well, every other time, you guys would be in class. Right now, there's a pandemic going on, so you're not. Every other time, this would work, but this is a special case. When you're dealing with 2D, it doesn't work. I know, no fun. So in order to get Fn, what do we have to do? Well, we have to take a look at the sum, and we go, okay, the sum of forces in the y is equal to Fn, which points up, Fay, which points up, and Fg, which points down. So it's going to be plus, minus. And then this will be 0. Why is it 0? Because I'm not going up, I'm not going down. The table is supporting the brick. So what this means is that Fn, which is what we want, is going to be equal to Fg minus Fay. But wait, I hear you say, Mr. C, when you were doing it earlier in the notes, you didn't have Fn and Fay on different sides. You had them on the same side because they were both pointing up. Yes, but that doesn't really help us, right? Like Fn plus Fay equals Fg, but I don't know what Fn is. I want Fn. So what do? Instead of writing it like this, like I did before, I just take this thing and I move it over here. And that allows me to solve for the Fn that I need in order to do the rest of the problem. So, well, Fay we have. We know that one. We solved it earlier. It's 75. Fg, we know how to solve that. That part's actually pretty easy, right? It's just 9.8 times 16. So 9.8 times 16, did I work it out? No, looks like I didn't. All right, I have to do it myself. Times 16 equals 156.8. So there you go. Now I have Fn. If I have Fn, I can put it in here, and then I can solve for F mu. And if I have mu, I can put it here. And if I've got that, I can do this minus this to get this, which lets me get A, finally. So now I go back and I fill everything in. 156 minus 75 equals 81.8. So this should be 81.8. 81.8 times 0.44 equals, so it should be 35.992. I should have rounded that, whatever. So that means that the sum of all forces is going to equal to negative, oops, sorry, not negative. It's going to be 94. That's close enough. Then I solve for the original question. 94 equals 16A. 94 divided by 16. I get A equals 5.87 meters per second squared. and it'll be positive. And there you go. There is the final answer. The method for doing this has remained the same. There's no change there. The only part that's different is how you assemble that answer. Everything on this side here, all of this is the same. This is the only change right here. This is the only part we have to keep track of. And we just have to realize that we're adding, right? There's 2 arrows up, 1 arrow down. I want to know how big each one is. That's all you got to do. Okay? Okay. So what happens if we make it point down? Right? That's the only other option. We can either have the force applied going up, or as I mentioned, it can be going down. So we're going to do exactly the same question, but we're just going to change the direction of the FA. So I come back here to my original picture, and I go like this. Erase, 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 erase. And I'm going to even keep the same numbers. This is going to go down, and this is 150 is force A. That means that this one and this one, we've got FAY and FAX. This is no different. Everything's the same, right? It's still cos, it's still 150, so it's still 130, 175. Okay, so 130 still goes here. Boom, done. That part's easy. Friction. That part will be different. Why will it be different? Well, not because of the coefficient, that part stays the same. Not because of the force of gravity, that part stays the same. This one is the only one that's going to be different, and even then, the number's the same. The sign is the only part that's different. The only part that I have to change is I have to go through and say, FAY is also pointing down because it is. So that means these two get added together. Force normal has to not only support the weight of the object pushed on the table, they also have to support your weight because you're pushing down on it. You're giving it a squeeze. It's got to support you, right? If it doesn't and you push down and it just collapses, then the table can't hold it. That's literally how that works. So this is the only change we have to make. It's no longer 185 minus 75, or sorry, 156 minus 75, it's now plus. So I go 75 plus 156.8 equals. That gives me 231. So this force normal is now 231. 232, basically. Why is it bigger? As I mentioned, because you're pushing down, the table has to push up harder. 232. That means this becomes 232. So I'm going to take 130 minus 232. Oh, no. I missed the step. 232 times 0.44. I need to make sure to include my coefficient of friction. 232 times 0.44 equals, there we go. This is 102.08. 30, so this will be 27.92. 27.92 divided by 16 is equal to 1.745. And there we go. What are we seeing? It's slower. You have to push harder if you wanted to keep the same speed because you're pushing down. You're increasing the strength of friction. You're making it more. There you go. The math is the same. The only difference is setting up the question. A single negative sign makes the difference. But just remember, everything to do with this stuff is about adding vectors. It's all the same. Nothing has changed with that. You're still just adding everything that points up and subtracting everything that points down. Or adding everything that points right and subtracting everything that points left. Whichever works for you, go for it. Okay? It's going to take some practice. I don't unfortunately have a copy of the booklet here, but there's quite a lot of practice. I made sure to put in a lot. Basically, you can keep going until you see something that says inclined planes. If you see inclined planes, you've gone too far. So continue working on things, see what you guys can do. I will probably do a video about inclined planes in next week, maybe Tuesday, and then you guys can continue working on stuff. So the hope is that we should be able to have a two-dimensional test maybe late next week or early the week after. Okay? But of course, obviously, as always, work at your own pace, no rush. Okay? All right, guys. I hope everyone's having a good time. I hope that the summer weather is agreeing with everybody, although it was a little chilly today. And I will see you guys next time.